In the previous videos, we learned how to name alkanes, both unbranched and branched, but all of the examples that we saw were straight chain alkanes. And you will find that alkanes can also be cyclic if they have 3 or more carbons. And in that scenario, we're going to use the prefix cyclo and then end with the regular alkane name. So you'll find it's a very repetitive system. So let's take a look at a few examples. Okay, this is not a triangle. Well, it is a triangle, but in this scenario, it's also an alkane. So I'm going to count the number of carbons, and then I'm going to give it a name. I see that it has 3 carbons. So if this was a regular straight chain alkane, we would call it propane. Ane indicating it's an alkane, prop indicating that there are 3 carbons. But because it's cyclic, we're going to give it the prefix cyclo. So that becomes cyclopropane. And that's pretty much it. So you'll find that this is very, very similar to naming regular alkanes. If I draw what looks like a square, there are 4 carbons in this example. So I want to use the prefix bute to indicate that there are 4 carbons. But because it's cyclic, I will start with cyclo, and I'll call it cyclobutane. And we can continue this with more and more carbons. This pentagon contains 5 carbons, so I'm going to call it cyclopent for 5, and ane for alkane, so that becomes cyclopentane. Next, we can have 6 carbons, which looks like a hexagon, and I'm going to call that cyclohexane, hex for 6 carbons. If there are 7 carbons, this one's a little trickier to draw, so I was kind of extended out over here to be a little bit wider, and then I bring it back in at the bottom. I will call that cycloheptane. So these are the same alkane names we saw earlier. They just have the prefix cyclo to indicate that they are cycles. And cycloalkane kind of looks like a stop sign. So draw your best version of a stop sign, just don't write stop in it. And that is cyclooctane. Note one difference between, well, there are many differences, but one distinct difference here between the organic and inorganic naming system is that here we don't drop that first vowel. So we just call it cyclooctane with both of those O's in there. One thing I would like you to note is that cycloalkanes and straight chain alkanes are not structural isomers. And this might feel a little unintuitive, but let's take a look at what these structures look like, and we'll count the number of carbons and hydrogens and everything and prove to ourselves that these are not structural isomers. I can't draw a square. Okay, good enough. So this is just standard butane straight chain version, 4 carbons connected in a row, exactly what we're used to. This is cyclobutane, so still 4 carbons, whoa, butane. Still 4 carbons, but now they're all connected to each other. I'm going to start by expanding these out. So I see that there are 4 carbons connected in a chain, and then I'm going to fill these in with hydrogens. Note that this carbon only has 1 bond right now, which means it needs 3 more bonds to fulfill its octet, and I'm going to fill those in with hydrogens. And the same thing applies to this carbon at the end since they are symmetric. The carbon in the middle has 2 bonds, which means it needs 2 hydrogens to complete its octet. And same thing on this carbon as well. If I go through and I count the carbons and the hydrogens, then I'm going to have the molecular formula C4H10. And then I'll do the same thing with cyclobutane. here I see that the carbons all connect to each other. So each carbon in this molecule already has 2 bonds, which means that each carbon only needs 2 hydrogens to complete its octet. And if I do the same thing here and I turn that into a molecular formula, I see that there are 4 carbons and 8 hydrogens. These are different molecular formulas. And this is why they are not structural isomers. So in order for molecules to be structural isomers, they have to have the same molecular formula, but different atom connectivity. Sure, here we have different atom connectivity, but the molecular formulas are not the same, so these are not structural isomers. And notice that the cycloalkane has 2 hydrogens fewer than the straight chain alkane, and that's always going to be that same pattern. So if you were to generalize these molecular formulas, your straight chain alkanes would be CnH2n plus 2, whereas the cycloalkanes would be CnH2n. So in this little n, I can just plug in how many carbons there are in this particular molecule. So in the straight chain alkane, we saw there were 4 carbons. And then I'm just going to multiply that 4 by 2 and add another 2. And if I do that, I generate C4H10. So this is the general formula for all of my straight chain alkanes. In the cycloalkanes, this would be C4H2 times 4, which becomes C4H8. So all the cycloalkanes will always have 2 hydrogens fewer than the straight chain alkanes.